Welcome to the Joy of Architecture.
Great to be diving in.
Today, let's dive straight into something that's just completely changed the game for cloud-native software. Data management, specifically in microservices.
That's absolutely right. I mean, when you shift from that one big central database, the monolith style, you get, amazing flexibility, fantastic scalability.
Oh, yeah.
But suddenly your data isn't neatly tucked away in one spot anymore. It's everywhere, distributed.
Exactly. You might go from one database to, dozens, maybe more, each owned by its own little service.
And that just fundamentally changes how you have to think about critical stuff like, data consistency and transactions.
Right. How do you keep everything in sync? How do you make sure an operation completes correctly when the data it needs is scattered all over the place?
That really is the million-dollar question. The old ways, the traditional database approaches, they just don't cut it in this new world.
So that's what this deep dive is all about. We've gone through a whole stack of sources looking at these exact problems.
And more importantly, the patterns and solutions that really smart people have come up with to tackle this complexity.
Yeah, our mission here is to sort of cut through the noise, pull out the key insights from all that material. We're going to unpack the most important data management and consistency patterns that you really need to know about.
We'll look at the foundational stuff like database per service and that related idea, polyglot persistence.
And we'll also touch on one you see a lot, maybe too much, the shared database.
Oh yeah, definitely need to talk about why that's usually an anti-pattern. We'll also cover scaling for massive data with sharding.
And the big one, how do you handle those tricky distributed business operations? That's the Saga pattern, right?
Exactly. Sagas are crucial.
Yeah.
So yeah, let's get into the details, understand the why behind these choices.
Okay, let's jump in. First up, database per service. This feels like microservices 101, but what's the absolute core concept?
It really boils down to ownership and encapsulation. The fundamental idea is each microservice owns and completely controls its own private database.
Private
Meaning no other service, absolutely none, can touch that database directly. Not allowed. Access has to go through the owning service's public API. That's non-negotiable.
So the database is effectively hidden, yeah. It's part of the service's implementation details.
Precisely. The sources really hammer this home. Encapsulation is key. Now, how you implement that can vary. There could be a totally separate server, maybe just a different schema on a shared server, or even just private tables within a schema.
But there have to be real barriers.
Yes, strong barriers. Think strict database user permissions, network rules, whatever it takes to enforce that API-only access rule.
Okay, makes sense. So why go to all this trouble? What's the big payoff?
The number one reason, loose coupling. If you want your services to be able to change their data structures, maybe even swap out their entire database technology.
Without breaking everything else.
Exactly. Without causing a ripple effect of changes across the whole system. This is how you do it. You avoid that nightmare scenario where one database schema change forces 10 teams to coordinate and redeploy.
Independence. Freedom for the teams.
That's a huge part of it. And it directly enables that other pattern we mentioned, polyglot persistence. Use the best tool for the job, database-wise, for each service.
Right.
Plus, you get other benefits like independent scalability, scale the order services database without touching the user services, and fault isolation. If one database crashes, it ideally only affects its own service.
Okay, those are pretty compelling advantages for building microservices. But, there's always a trade-off. What's the catch here?
Oh, for sure. The biggest, most significant trade-off is dealing with business processes or queries that need data from multiple services.
Because you can't just join tables across databases anymore.
Nope. Forget about those simple multi-table AC transactions you used to write. If updating an order needs to also update inventory and maybe customer loyalty points, well, that now involves 3 separate services and their databases.
And that
means you need more complex patterns like sagas, which we'll get to manage that whole process and ensure consistency eventually. It's definitely not as simple.
And just querying data across services must be slower too.
Correct. You're making API calls instead of running a SQL join. That adds network latency. Or you have to build potentially complex workarounds like API composition layers or materialized views.
Plus just more databases to manage.
Yeah, the operational overhead goes up, more backups, more monitoring, more patching, potentially more database types to understand.
So it sounds like the core trade-off is you gain autonomy, you gain independent scalability.
But you lose that immediate simple consistency and you take on more complexity, especially for cross-service operations and overall management.
Right. Consistency across the whole system often becomes eventual, not instantaneous.
Hmm.
Latency for those cross-service hops goes up, but the scalability per service can be really high.
That sums it up pretty well.
How do the big cloud players support this? Are they geared for it?
Absolutely. They're built for this model.
Mm-hmm.
Think about AWS. They have RDS for relational,
Hmm.
Aurora, DynamoDB for NoSQL, Elasticache, Neptune for graph. A whole zoo of options. You use them with Lambda, ECS, EKS, whatever.
And they push things like IAM policies to lock down access.
Exactly. Azure's guidance is super explicit. Each service manages its own data. They offer Azure SQL, Cosmos DB, which is multi-model itself, Redis cache, and so on.
GCP, the same.
Yep. Cloud SQL, Spanner for global consistency, Bigtable, Firestore. They all provide this diverse portfolio precisely because they expect you to use database per service and likely Polyglot Persistence. Same in the open source world, mixing PostgreSQL, MongoDB, Cassandra, Redis is standard practice.
If you were to draw this, what's the picture?
It's like a collection of separate islands. You draw service A connecting only to its own little database A island.
Yeah.
Service B only to DBB. Service C only to DBC.
No bridges between the island's database.
And none directly to the databases. You show arrows between the services representing API calls, but never an arrow from service A directly into DBB's data store. It visually screams separation.
Okay. Now, the operational side. Managing, say, 50 databases, maybe 10 different kinds, sounds daunting.
It is a significant challenge, no doubt. Data governance gets trickier. How do you ensure standards or discover data across all these different stores?
And seeing the whole picture.
Observability is key. You need centralized logging, metrics, and especially distributed tracing to follow requests as they hop between services and databases. Failure handling means distinct backup, restore, and disaster recovery plans for each different kind of database you use.
Data lineage, figuring out where data came from and where it went, must be harder too.
Much harder. Schema management is independent per service, which speeds up development, but you have to be really disciplined about API versioning so you don't break consumers.
And just keeping all those databases provisioned, patched, monitored.
Automation. Automation is absolutely non-negotiable. You can't manage that diversity manually at scale.
So, best practices boil down to
Aligning services with business capabilities, like domain-driven design suggests, clear ownership, strict API-only access. Choosing the right granularity, maybe a schema per service is okay sometimes, doesn't always have to be a whole server.
and investing heavily in the ops side.
Crucial. Robust data operations, backup, recovery, monitoring, and solid automation and observability. Plan for how you'll integrate data across services when you need to.
And the big no-no, the anti-pattern.
Direct database sharing is the cardinal sin here. Also, ignoring the complexities of distributed data, underestimating the operational burden, or making synchronous calls between services that directly hit another service's database, those are all recipes for trouble.
Any famous examples of companies doing this well?
Pretty much any large-scale tech company you can name. Netflix is famous for it, using Cassandra, CockroachDB, MySQL, you name it. Amazon, obviously, both their e-commerce and AWS are built this way. Spotify, eBay, Uber.
They all have services owning distinct data stores.
Yes, often using a mix of technologies. The big learning from them is that making this work at scale requires, well, mature engineering practices, really strong operational capabilities, and using those complementary patterns, like Sagas, effectively.
Okay, let's pivot to that anti-pattern you flagged, the shared database. You see this sometimes, especially maybe in migrations. Why is it generally considered bad news for microservices?
Right, the shared database. It's literally what it sounds like. You have multiple different microservices all reading from and writing to the exact same database instance. Often the same schema, even the same tables. The database is just a common utility.
The complete opposite of data goes per service. Why would anyone do this if it's an anti-pattern?
Honestly, the sources suggest you generally shouldn't, especially not long-term. It pops up often out of, let's say, expediency or necessity, usually intended as temporary.
Like for a startup, just getting going.
Maybe very small startup, yeah. It looks simpler initially, less operational overhead at first, but it's almost always accumulating technical debt if you expect to scale or evolve quickly.
Or during a migration.
Very common there. You're breaking a monolith into services, but maybe they still talk to the old big database for a while. It's an interim step. The danger is getting stuck there.
Ending up with a distributed monolith.
That's the term, yeah. Or sometimes there are legacy constraints or a perceived overriding need for immediate, strong ACID consistency across data that really should be in separate services,
Hmm.
which often just means the service boundaries were drawn wrong in the first place.
So really a compromise or a temporary state, not a target architecture.
Exactly. The sources are pretty unanimous.
Mhm.
Do not adopt this as your long-term strategy if you want the real benefits of microservices, agility, independent scaling, resilience. It undermines the core principles.
What are those tempting initial benefits, though? Why does it feel easier at first?
Well, transactions within that single database are easy. Standard ACID. Joining data is simple SQL. You don't have immediate data redundancy issues. Initial development and deployment might feel faster because it's familiar territory.
Okay, but the downsides must be huge if it breaks the model.
Massive. The absolute killer is tight coupling. Services become glued together at the database level.
Oh.
Development time coupling. One team changes the shared schema, and it breaks three other services. Runtime coupling. Services contend for the same database locks, CPU I/O. One service hammering the database slows everyone else down.
And scalability.
Forget about independent scalability. The shared database becomes the bottleneck for all connected services. You lose autonomy, you lose technology choice. Everyone's stuck with the same database tech.
Polyglot persistence is out the window.
Completely. And it's
Yeah.
a massive single point of failure. If that shared database goes down, all those services are dead in the water.
So that's the distributed monolith. You've distributed the application code but kept the monolithic data bottleneck and coupling.
Precisely. You get the operational complexity of running multiple services,
Hmm.
but none of the development flexibility or independent scalability. Consistency is strong inside that one database, sure, but autonomy and scale are shot.
What does the diagram look like for this one?
It's starkly different from database per service. You draw multiple service boxes, A, B, C, and they all have arrows pointing directly into one single central shared database box. It visually screams bottleneck and dependency.
Ouch. Operationally, what are the headaches?
Well, schema management requires painful cross-team coordination and becomes a bottleneck itself. Performance tuning is a nightmare. Optimizing for one service can hurt another. Trying to figure out which service is causing database load is hard, the classic noisy neighbor problem.
And failure.
That single database failing takes down all dependent services. Resilience is much lower. Security is also complex. Who do you give fine-grained permissions within that shared space?
Okay, so if you're forced into this, maybe during a migration, what are the least bad practices? Mitigation tactics.
Right, damage control. Try to create logical separation using database schemas if possible. Implement very strict access controls. Maybe services can only write to their own schema or tables, even if they can read others.
Try to enforce API thinking even internally.
Yeah, encourage services to call each other's APIs rather than querying the shared database directly, even if it feels redundant initially. Use views for read-only access to other services' data. But the most important thing, have an active funded plan to get off the shared database and move towards proper database per service.
And the anti-patterns are basically just doing it long term.
Pretty much. Using it as the final architecture, allowing uncontrolled direct database access between services. Ignoring the coupling it creates, not having that exit plan. Building that distributed monolith without realizing it until it's too late.
Any success stories? Or is it mostly horror stories and migration tales?
It's overwhelmingly presented as a cautionary tale in the context of microservices. You hear about it during monolith decompositions, but often the outcome is still that tightly coupled distributed monolith if they don't fully decentralize the data.
What do the experts say?
Thought leaders like Martin Fowler, Sam Newman, Chris Richardson, they all strongly advise against it. They highlight the lack of encapsulation, the schema evolution problems, the coupling. It's widely recognized as an anti-pattern for achieving microservice goals.
Okay, message received on that one. Let's move to something that sounds more positive. Polyglot persistence. We touched on it, but let's define it properly.
Polyglot persistence is really just the idea of using multiple different database technologies within a single application or system. It's not tied only to microservices, but it fits perfectly there.
So in microservices, it means each service team picks the best database for their specific job.
Exactly. Service A needs strong transactions, so it uses PostgreSQL. Service B needs flexible schema and high write volume, maybe it uses MongoDB or Cassandra. Service C needs super fast key lookups, it uses Redis. Service D manages complex relationships, it uses Neo4j.
Using the right tool for the right job, but at the database level. When does this make sense?
It makes sense when your services genuinely have diverse data requirements. Different data models, different read-write patterns, different query needs, different scaling requirements.
Like needing transactional integrity for orders, but maybe a document store for product catalogs and a search engine for search.
Perfect examples. Or needing a graph database for recommendations, a time series database for metrics, an in-memory cache for sessions. You leverage the specialized features and performance characteristics of different database types.
What are the big wins?
Optimized performance is a key one. The database is tailored to the workload. Better scalability, as each type scales in the way it's best suited for. Increased flexibility and agility for development teams. Potentially even cost effectiveness if you're matching resources to needs precisely.
Sounds great. What's the flip side? What are the trade-offs?
The main one is increased operational complexity. You now have multiple different database systems to provision, manage, monitor, backup, secure, and patch.
Need more skills on the team.
Definitely. You need expertise across potentially several different database technologies. Data integration between these heterogeneous stores becomes a significant challenge. How do you join data or maintain consistency? Tooling can become fragmented. CI/CD pipelines get more complex.
So you trade operational simplicity and consistency guarantees for tailored performance and functionality.
That's a good way to put it. Consistency between the different databases is typically eventual, managed via application logic or eventing. Latency within a service might be lower due to the optimal DB choice, but cross-database operations add that integration complexity. Scalability is high per component, but managing the diverse fleet is the work.
And the cloud providers, as we said, they actively encourage this.
They absolutely do. AWS talks about purpose-built databases and has over 15 engines. Azure highlights Cosmos DB's multi-model capabilities alongside SQL DB, Cache for Redis, etc. GCP has its portfolio, Cloud SQL, Spanner, Bigtable, Firestore. They want you to mix and match.
What does the architecture diagram look like here?
Similar to database per service, showing separate services connected to their own databases. But the key difference is that the database boxes would be explicitly labeled or visually distinct. PostgreSQL, MongoDB, Neo4j, Redis, Elasticsearch, clearly showing the technological diversity. Communication between services still happens via APIs, or maybe a message queue.
Operationally, this sounds like it requires serious maturity.
It really does. Data governance needs a unified approach across different technologies, which is hard. Observability requires aggregating logs and metrics from all these different systems. Distributed tracing becomes even more vital.
Disaster recovery.
More complex. Each database type has unique failure modes and backup recovery procedures. Your overall DR plan has to account for this mix. You need the right skill sets, consistent security policies across different models, careful cost management, and robust data integration pipelines, ETL, event streams, between the stores.
Best practices for managing this complexity.
Selection must be driven by genuine technical need, not just wanting to play with a new toy. Invest in training or hiring the right expertise. Try to standardize on a limited set of preferred databases where possible. Don't let it become total chaos.
Governance is key.
Strong data governance across everything. Automate provisioning, monitoring backups like crazy. Centralize observability as much as possible. Plan data integration early. Maybe adopt new databases incrementally.
And the anti-patterns.
Choosing tech just for resumes, resume-driven development, grossly underestimating the operational overhead, cost, or skill requirements. Having no governance or standards. Failing to plan for data integration. Not having the necessary expertise. Or, conversely, forcing everything into one database type when Polyglot would genuinely be a much better technical fit.
Who's famous for using this well?
Netflix is the poster child. They use a huge variety. MySQL, CockroachDB, Cassandra, Easy Cache, Elasticsearch, Janus Graph, and more, each chosen for specific workloads like billing, global state, viewing history, caching, search, recommendations. Amazon, Facebook Meta, many large e-commerce platforms, mixing relational for orders, document for catalogs, cache for carts, search index, financial institutions. The lesson is, it works incredibly well for complex, high-scale systems with diverse needs, but it demands that mature engineering culture, strong ops, and strategic management. Don't underestimate the hidden costs in tooling, processes, and people.
Okay, let's switch gears to pure scale. What about when one data set just gets too massive for a single database? Even the right kind. Let's talk sharding.
Right, sharding. This is about horizontal partitioning.
Mm.
You take what is logically one very large database, maybe billions of user records, and you physically split its data across multiple independent database servers called shards.
Each shard holds just a piece of the total data.
Exactly. Each shard holds a subset of the rows, but typically has the same table structure, the same schema.
How does the application know which shard has the data it needs? Like,
Yeah.
user 123 is on shard 5.
Through a shard key, sometimes called a partition key. It's a specific column or field in your data, often something like userid, customerid, tenanted. When a request comes in, some routing logic looks at the shard key value in the request and uses a function or a lookup table, a shard map, to figure out exactly which shard holds that user's data.
When do you reach for sharding? Is it a last resort?
It's definitely for when you hit serious scale limitations. Massive data volumes that just won't fit or perform on a single server, no matter how powerful. High throughput needs, reads or writes, exceeding what one node can handle. When vertical scaling, buying bigger, faster hardware, becomes prohibitively expensive or impossible.
Any other reasons?
Sometimes for availability. If one shard fails, it only impacts the subset of data on that shard, not the entire data set. Or for geographic distribution, placing shards closer to users in different regions for lower latency or data residency compliance.
Benefits seem clear scale, performance, availability.
Yes, the primary benefit is horizontal scalability. Need more capacity, add more shards, typically on commodity hardware. Performance often improves because queries run against smaller data sets on each shard. Availability can increase due to failure isolation.
But the trade-offs sound complex.
They are significant. The biggest headache is dealing with queries or transactions that need data from multiple shards. These cross-shard operations are often slow, complex to implement, and can negate the benefits.
Choosing that shard key sounds crucial too.
Absolutely critical and difficult to get right. A poor shard key leads to uneven data distribution. Some shards get overloaded, hotspots, while others are idle. And changing the shard key later is usually extremely difficult.
What about rebalancing if data does get skewed?
That's another major operational challenge.
Hmm.
Periodically, you might need to split shards, merge shards, or move data between them to keep things balanced. This is often a complex, potentially disruptive process. You also lose some database conveniences like easy enforcement of global uniqueness or foreign keys across shards.
So again, trading simplicity for massive scale.
Pretty much. Consistency is usually strong within a single shard, but achieving strong consistency across shards is hard, often requiring things like two-phase commit, which harms availability, or accepting eventual consistency for cross-shard operations. Latency is great for single-shard queries, potentially bad for cross-shard. Scalability is the huge win.
How do you implement this? Do databases handle it?
It varies. Some databases have built-in sharding support. MongoDB and Cassandra are well-known examples. Azure Cosmos DB and AWS DynamoDB partition automatically based on your partition key. GCP's Cloud Spanner handles splitting automatically too.
What about traditional relational databases?
For something like PostgreSQL or MySQL, you often implement sharding at the application level or use middleware. Vites is a popular open-source solution for sharding MySQL. Azure SQL has client libraries to help manage application-level sharding.
What would a diagram look like?
Typically, you'd show the application or a client talking to a dedicated routing logic component.
Oh.
This component takes the request, inspects the shard key, maybe consults a shard map database, and then directs the request to the correct database shard box. Shard 1, shard 2, shard n.
Operationally, sounds like a lot to manage.
A lot.
Yeah.
Provisioning, patching, monitoring dozens or hundreds of shard instances. Keeping that routing logic highly available and performant. Dealing with rebalancing, developing scripts or processes for splitting or merging moving data without downtime.
Schema changes.
Have to be rolled out carefully and consistently across all shards. Backup and recovery needs to happen per shard, but you might need coordination for point-in-time recovery across shards. Monitoring is critical, tracking performance, disk space, hotspots on every single shard. Automation isn't optional, it's mandatory.
Best practices for sharding.
Choose that shard key very carefully. Aim for high cardinality, even distribution, and something that doesn't change. Design your application to make most operations target a single shard, denormalize data if needed. Plan for rebalancing from day one. Build or use robust routing. Automate everything. Consider managed sharding solutions from cloud providers if they fit.
And what should you absolutely avoid? Anti-patterns.
Picking a bad shard key is the classic mistake. Designing applications that constantly require cross-shard joins or transactions that defeats the purpose. Ignoring rebalancing until it's a crisis. Trying to manage hundreds of shards manually. sharding too early when simpler scaling methods would work, letting shard key values change.
Any real-world examples?
Huge scale systems rely on it. Social media platforms shard user data and posts by user ID or region. E-commerce sites might shard product catalogs or order data. Gaming companies shard player data or game worlds. Specific examples like Tinder sharding by user ID or Uber sharding by trip or rider ID come up. The main learning is it's essential for extreme scale, but success hinges on that shard key and rock-solid operational automation.
Okay, finally, let's address the elephant in the room for distributed systems: transactions. How do you handle business operations that need to update data across multiple services consistently? Enter the Saga pattern.
Right, the Saga pattern. Since you typically can't use traditional distributed transactions like two-phase commit or 2PC across independent services with their own databases because they're often unavailable, slow, or not supported by NoSQL databases, you need another way.
And a Saga is that way.
It's the predominant pattern. A Saga manages a sequence of local transactions. Each step in the sequence is just a normal atomic A to D transaction executed by a single service against its own database.
Okay, a sequence of local transactions. What happens if one fails halfway through?
That's the crucial part. If any local transaction in the sequence fails, the Saga executes a series of compensating transactions to undo the work done by the preceding successful local transactions.
Ah, so it's not atomic commit, it's commit then compensate if needed.
Exactly. It ensures business consistency eventually by either completing all steps successfully or by rolling back the already completed steps if a later step fails. It achieves semantic atomicity for the business process, even if not technical atomicity.
How is the sequence actually managed? Who tells the services what to do?
There are two main coordination approaches, orchestration and choreography.
Orchestration.
Orchestration uses a central coordinator, the Saga orchestrator. It explicitly tells each service what local transaction to execute, waits for the reply, and if it gets a failure, it then explicitly tells the preceding services to execute their compensating transactions. It's like a conductor leading an orchestra.
And choreography.
Choreography is event-driven. There's no central coordinator. Each service, after completing its local transaction, publishes an event. Other services listen for relevant events and trigger their own local transactions based on those events. If a service fails, it might publish a failure event, which triggers compensating actions in services that listen for it. It's more like dancers reacting to each other's moves.
When do you absolutely need sagas?
You need them whenever you have a business requirement for data consistency across a process that spans multiple microservices, especially when using the database per service pattern. Also essential for long-running business processes, where holding database locks for the entire duration, like in 2PC, would kill availability and performance. Basically, it's the standard way to handle reliable distributed business operations without resorting to 2PC.
What are the benefits of using sagas?
Well, the main one is it allows you to maintain business data consistency across decoupled services. You get loose coupling services. Don't need to know about each other's internal transaction logic, just the commands or events. Availability and resilience tend to be higher because you're only doing short local transactions, not holding long distributed locks. Scalability is good as services scale independently.
Sounds essential. What are the downsides? It feels like it could get complicated fast.
It definitely increases complexity significantly. Designing and implementing the compensating transactions correctly can be very tricky. What does it mean to undo? Adding an item to a shopping cart if the payment fails. Maybe you just remove it, maybe you mark it as canceled.
Idempotency must be important too, making sure retrying an operation doesn't mess things up.
Absolutely critical. Both the forward local transactions and the compensating transactions must be idempotent, because in a distributed system, messages can be delayed or redelivered. You might try to charge a credit card twice or issue a refund twice if your operations aren't idempotent.
And just figuring out what went wrong.
Debugging and observability are major challenges. Tracing a single business transaction across multiple asynchronous service calls and potential compensation steps requires really good tooling, distributed tracing, correlation IDs, centralized logging. You also have to accept eventual consistency. The system might be in an inconsistent state temporarily while the saga is running or compensating. Reads during this time might see intermediate states.
Okay, so impact. Consistency is eventual for the whole operation. Latency depends on the number of steps and communication hops. Scalability is high because it avoids distributed locks.
That's a good summary.
How do cloud platforms help implement sagas?
They offer services that are well suited for both coordination types. For orchestration, state machine services are ideal. AWS Step Functions, Azure Logic Apps, or Durable Functions, Google Cloud Workflows. They manage the state, retries, and compensation logic flow.
And for choreography.
Messaging systems are key. AWS SNS SQS, Azure Service Bus or Event Grid, Google Cloud PubSub, or open source options like Apache Kafka or RabbitMQ. These provide the backbone for services to publish and subscribe to events. Frameworks like Eventuate Tram also help atomically publish events alongside database updates.
What do the diagrams look like?
An orchestration diagram shows that central Saga orchestrator box sending command messages like process payment to service boxes, payment service, and receiving replies. If a failure reply comes back, the orchestrator sends compensating commands, refund payment, to the relevant services.
Choreography.
Choreography shows service boxes interacting only via a central message broker box. Order service publishes order created. Payment service consumes it, processes, publishes payment processed. Inventory service consumes that, publishes inventory updated. If payment service publishes payment failed, order service consumes that event and triggers its compensation logic.
Operationally, what do you need to worry about?
For orchestration, the orchestrator's state needs to be stored durably and highly available. For choreography, managing correlation IDs to track which events belong to which Saga instance is crucial. As mentioned, observability is paramount. Distributed tracing, logging with correlation IDs, monitoring Saga's success failure rates, durations, queue lengths,
And failure handling.
robust retries with exponential backoff for transient errors, clear logic to trigger compensation for permanent failures. And you need a plan for what happens if a compensating transaction itself fails, often requiring manual intervention or alerts. Idempotency testing is vital.
Best practices for sagas.
Keep the local transactions within each step short and focused. Make sure compensating actions are well-defined, reliable, idempotent, and thoroughly tested. Designed for failure from the outset, use correlation IDs universally. Idempotency, idempotency, idempotencies. Can't stress it enough. Choose your coordination strategy wisely based on complexity and coupling tolerance. Consider techniques like semantic locking if you need to prevent reads of intermediate states. Monitor everything.
And the anti-patterns to avoid.
Having undefined, untested, or unreliable compensating actions is probably the worst. Making sagas too long or complex, involving too many services. Ignoring idempotency. Lack of observability, making debugging impossible. Trying to use sagas for read operations, it's a right transaction pattern. Creating cyclic dependencies in choreography, event spaghetti. Using blocking calls within saga steps. Putting too much business logic inside the orchestrator instead of in the services.
Any well-known case studies?
E-commerce order processing is the classic example. Everyone uses coordinate order, payment, inventory, shipping, with compensations like refunding payment or releasing inventory stock. Financial services use them for multi-step transfers or approvals, travel booking sites, coordinating flights, hotels, rental cars. Uber has talked about using sagas, but also highlighted the significant debugging challenges they encountered with very complex write flows. Netflix uses workflow engines like Conductor, which naturally implement orchestrated sagas for processes like booking trips. The consistent learning from production use is, you need fantastic observability, and you must get idempotency right everywhere.
Wow. Okay, that was a whirlwind tour through some absolutely critical patterns for handling data in modern distributed systems.
It really underscores the fundamental shift, doesn't it? Moving away from that single source of truth changes everything. You gain that amazing flexibility and scale.
But you absolutely have to adopt new patterns to manage the resulting complexity, especially around consistency and coordination across service boundaries.
Exactly. Database per service and Polyglot Persistence give you the isolation and optimized storage. Sharding lets you handle truly massive datasets.
But those choices immediately force you to confront distributed consistency, which is where sagas come in as the way to manage business transactions reliably without 2PC.
And we saw the shared database as that cautionary tale. What happens when you try to get the microservice structure without embracing the necessary data separation?
Yeah, and a key theme is that none of these are free lunches, right? They all involve significant trade-offs.
Definitely. You're often trading that comfortable world of immediate global consistency and operational simplicity for long-term agility, independent scalability, and resilience. It's a conscious architectural decision.
And success clearly depends on more than just picking the right pattern name. It requires deep investment in those complementary practices.
Robust observability, pervasive automation, extremely careful design, especially thinking about failure modes, idempotency, compensation logic for sagas, shard key selection for sharding, is a whole ecosystem of practices.
Understanding these patterns and their implications feels absolutely essential for anyone building or evolving systems today.
Couldn't agree more. It's the reality of building scalable, resilient applications in the cloud-native world.
Well, thanks for joining us on this really insightful deep dive. It's a complex landscape for sure, but breaking down these patterns definitely helps make sense of it.
My pleasure. It's a fascinating and constantly evolving space.
And just to leave you, our listener, with something to chew on. As our systems become ever more distributed, is that old idea of a single, global, instantly consistent source of truth becoming, well, a relic, an outdated ideal?
Mm.
And if it is, the really important question becomes how much eventual consistency, how much temporary inconsistency between different parts of your system are you and your business stakeholders truly comfortable with? Thinking through the real world impact of that eventual nature is just as critical as choosing the right database or pattern.
That's a really powerful thought to consider. What does consistency really mean for your specific domain?
Definitely something to mull over. To keep exploring these kinds of architectural challenges and patterns with us, please make sure you subscribe to The Joy of Architecture.
We hope you'll join us again for our next deep dive.